Good morning everyone. Today we are going to see about mechanics, which comes for the third BSc Mathematics students. Mechanics is the area of mathematics and physics concerned with the relationship between force, matter and motion among physical objects. Forces applied to objects result in displacement or change of an object position relative to its environment. In simple words, mechanics deals with energy and forces and their effects on other bodies. Let us see the unit-wise classification. Before that, we have to see about the great mathematician Röntgen, who was the first to draw up a treatment of mechanics with the aid of geometry. He first distinguished harmonic progression from arithmetical and geometrical progression. He was the pioneer to give principles of mechanics. He gave a satisfactory explanation of the coincidence between the lunar period of rotation and revolution. Now let us see the unit-wise classification. First of all, we will see the introduction of mechanics. Mechanics, the relationship between mechanics and mathematics, some important applications of mechanics on mathematics. Mainly we are going to see about the hanging strings and the mathematical concepts involved in equilibrium of a uniform homogeneous string, the definition of span and sag, and the concept of suspension bridge. So mechanics is a branch of the physical sciences. As we stated already, it is concerned with the state of rest or motion of bodies that are subjected to the action of forces. The study of mechanics involves many more subject areas. However, initial study is usually split into two areas, statistics and dynamics. Statics is concerned with bodies that are either at rest or move with a constant speed in a fixed direction. So from the name statics, it deals with the objects which are in rest position. Whereas dynamics deals with the accelerated motion of bodies, that is the objects which are in motion. Statics can therefore be considered as a special case of dynamics where the acceleration is zero. In engineering, since many objects are designed with the intention that they are at rest or other motions remains constant, statics deserves a special treatment in the study of mechanics. So here we are going to see about hanging strings. So we are going to see what is span and sag. Here we consider the equilibrium of an inextensible uniform homogeneous string hanging freely under gravity with its ends tied into 2 points. So in this diagram we can see two pillars in that a string tied to the strings. The distance between the string, that is the two pillars, is called a span. So here we can see the string. The depth of the string is called sag. The conductor medium is a string here. The portion below the sag is called ground clearance. So here AB are the points of suspension in the same horizontal line. AB is called span and the depth of C. Below AB is called sag. So here just see the diagram. We can see the two pillars standing and the string is tied to two pillars. A and B are the points of suspension in the same horizontal line. Here the distance AB is called span. And the red color dotted line, it is called sag. Next, span. Sag is directly proportional to the square of the span length. Longer span gives more sag. Tension. The sag is inversely proportional to the tension in the conductor. Higher tension increases the stress in the insulators and supporting structures. In this diagram, we can see AB are not in the same vertical line. AB are at two different heights. So here H is the height and O is the center point of the string AB. Next. So here we are going to prove that the shape of a uniform string hanging under gravity is a catenary equation. So we are going to the further assumptions. Let A and B be the points of suspension not lying in the same vertical line. C is the lowest point of the string. Q is the point of intersection of the tangent at C and P. And psi is the angle between these tangents. Let S be the length of the arc CP. Let us now clearly see diagrammatically. Next. So in this diagram, here AB is a string. Draw a line through AB. Here AB is a point of suspension not lying in the same vertical line. C is the lowest point of the string. Q is a point of intersection of the tangents at C and P. And psi is the angle between these tangents. Let S be the length of the arc CP. From this diagram here it is clear that there is three tensions acting in that T, T0 and the weight SW. The tension acts at 3 points throughout the suspension bridge. then the applied forces acting on the portion Cp of the string are the tension T at P along the tangent, the tension T naught at C along the tangent, the weight SW acting below through Q, where W is the weight per unit length of the string. So here clearly there are three types of tensions acting along the suspension bridge. Let the length of the string whose weights equals T naught be C, then T naught equal to Cw. Now the portion Cp is in equilibrium. So the sum of the horizontal components of the applied forces on Cp is 0. Also the sum of the vertical components of the applied forces is 0. So just remember that you use cos for horizontal component and sin psi for vertical components. So here the sum of the horizontal component of the applied forces on Cp is 0. Therefore we get T cos psi minus T naught equal to 0. When the vertical components of the applied forces is 0, we get T sin psi minus Sw equal to 0. So T cos psi equal to Cw, because we have already seen that tension T naught equal to Cw. So substituting Cw in for T naught, we get T cos psi equal to Cw and T sin psi equal to Sw. So now we are going to divide the second equation by the first equation. So sin by cos equal to tan, you will get S by C equal to tan psi. So S equal to C tan psi. So the remaining elements get cancelled. This is the intrinsic equation of the shape of the string, but this equation represents a catenary, isn't it? C equal to tan psi represents a catenary. So while we are taking the horizontal component 0 and vertical component 0, we get the shape of the string is a catenary. So we have proved that the shape of the string hanging in a suspension bridge is a catenary equation. So from this we further proceed to the remarks. We got T cos psi equal to Cw. It gives the tension at any point psi on the string is T equal to Wc secant psi, because T equal to Cw 1 by cos psi, 1 by cos psi is secant psi. So going to the definition of vertex and directrix. C is the vertex of the catenary and the horizontal line at the depth C, below C is the directrix of the catenary. So next we are going to attain the equation of the curve formed by the string in parametric form and Cartesian form. So we are going to prove that the parametric form x equal to C log secant psi plus tan psi and y equal to C secant psi, and the Cartesian form, in the Cartesian form we are going to prove that y equal to C cos h x by C. So here we are going to start with the assumptions. Let O be the point vertically below C at a distance C. Let OX and OY the horizontal and vertical lines in the plane of the string. Let it be x and y axis. Note that OX is the directrix of the catenary. Now listen to the diagram. Here we can see the string hanging along the axis. Just represent it graphically, x axis and y axis. Here P is the point P of x comma y, and the angle formed is psi. Capital C is the lowest point of the string and small c is the distance below capital C. The parametric equation of the string may be obtained from calculus result. So first of all, let us consider that dx by ds equal to cos psi, taking the horizontal component, and dy by ds equal to sin psi, that is taking the vertical component. Now the parametric form equation is derived as follows. Remember, already we got the catenary equation from the bookwork 1 as S equal to C tan psi. So first to take the first equation, consider dx by ds equal to cos psi. Now multiply and divide by d psi. Dx by d psi into d psi by ds equal to cos psi. Now you have to again find dx by d psi. So dx by d psi equal to cos psi into ds by d psi. So already we know that S equal to C tan psi, isn't it? So while differentiating S, we get C is a constant, so C. Tan psi differentiation is secant square psi. So altogether we get dx by d psi equal to cos psi C into secant square psi. Now integrate on both sides. So integrating we get integration of dx equal to C integration of secant psi into d psi. So integration of dx is Cx. So C is constant. Integration of secant is log secant psi plus tan psi. So again we will get a constant capital A. Now next consider the next equation dy by ds. The computation is a similar process. Dy by ds equal to sin psi. Again multiply and divide by d psi. So dy by d psi divided by d psi by ds equal to sin psi. dy by d psi equal to sin psi into ds by d psi. So sin psi, while differentiating s with respect to psi, we get c secant square psi. So altogether we get dy by d psi equal to sin psi c secant square psi. Now we have to integrate on both sides. So integration dy equal to c integral tan psi secant psi d psi, y equal to c secant psi plus another constant, so we get b. So now we have to find the value of the constants a and b. Put x equal to 0 and y equal to c, and the angle psi is 0. So we'll get the constants a and b are 0. Therefore, we get the conclusion x equal to c log secant psi plus tan psi and y equal to secant psi, because the constants a and b becomes 0. Next, coming to the second derivation, x equal to c log secant psi plus tan psi. So since we have the log, we take exponential on both sides. So e power x by c equal to e power x equal to c e power log secant psi plus tan psi. So e power x by c equal to secant psi plus tan psi. Take it as first equation. Considering its reciprocal, e power minus x by c equal to 1 by secant psi plus tan psi. So multiply by its conjugate. So secant psi minus tan psi divided by secant psi minus tan psi. So in the numerator you get secant psi minus tan psi by secant square psi minus tan square psi. So a term gets cancelled, and finally you get secant psi minus tan psi. Take it as second equation. Now add the first equation and second equation and divide by 2. So e power x by c plus e power minus x by c divided by 2. So you will get secant psi, or cos h x by c equal to secant psi, because e power theta plus e power minus theta is cos h theta. So e power x by c plus e power minus x by c by 2 equal to cos h x by c equal to secant psi. But we already know that y equal to c secant psi. Thus we have the Cartesian equation y equal to c cos h x by c. So before moving to the next module, we have to learn the importance of mathematics in mechanics. So where all the mathematics is used in your everyday life. Maths is very useful in everyday life. It is used in managing money, balancing the checkbook, shopping for the best price, preparing food, figuring out distance, time and cost, understanding loans, understanding sports, playing music, banking and whatnot. It is used in every core of the daily life. So predicting the weather. Fluids like the atmosphere follow a set of rules called the Navier-Stokes equation. Unfortunately, we do not know a direct solution of this equation. Instead, supercomputers divide the entire atmosphere into millions of blocks, each around 1 cubic kilometer in size, and use numeric simulations to create a high resolution forecast. It is used in MRI and topography, in medicine field also. The mechanics is used in medical fields such as MRI scanners and tomography machines. MRI scanners can create 3-dimensional images of the human body by taking countless 2-dimensional snapshots from different directions. The process of recovering the original 3-dimensional model using these snapshots is called tomography, and it wouldn't work without advanced mathematics such as radon transforms. Mathematics is quite literally saving lives. The next application of mathematics is in internets and phones, whereas it is used in the modern gadget also. The principle of queuing theory is used in internets and phones. Next, epidemic analysis. Again, coming to the medical field. As we have come across the pandemic corona, we can see how mathematics is used in epidemic analysis. When a new epidemic starts, one can fear that it will not stop since there are always new cases. It is not what mathematics says. From the value of R naught, we can decide, that is, we can come to a conclusion whether to give enough vaccine or to stop the vaccine. If the R naught value is less than 1, then the epidemic dies. While if R naught is greater than 1, then certain vaccines are necessary to given to everyone. The goal is to use these resources to decrease R naught below 1. It is used in satellite navigation also. To determine any location on Earth, GPS is used from satellites, which provides extremely accurate times. A metric space is a mathematical generalization of measuring distances. Because of general relativity, GPS receives have to use the Kerr metric rather than the usual Euclidean metric. It is used in codes and communication. Next. Now here we can see the suspension bridge, the role of mechanics in building bridges. Suspension bridges are elegant bridges that span distances between 300 and 2300 meters. Their flexibility and low dead weights are great for engineering. These same qualities are also liabilities. Suspension bridges are actually quite flexible to prevent buckling. These flexibility causes also means these bridges are susceptible to resonance. Resonance is a phenomenon modeled using second order differential equations. It is used in digital music also. Next. It is used to crowd control. Next. It is used in computer games. Next. It is used in movie graphics. Similarly, we can see a lot of application of mathematics in rockets and the satellites. Mathematics presents various clever algorithms to encode data in a way that you can detect and even correct a certain amount of errors. We can clear the noise after transmission. It is used in microwaves also. It is used to calculate the population dynamics. We can use calculus to control the population dynamics. Next, the application of mathematics in robotics. Here we can find the length detection, how a machine grabs the object using geometry, move the arms with using trigonometry, find distance from an object. Next, so applications. With circles and trigonometry, we can manipulate a joint arm to reach any point within a semicircle. A simple concept of the formula of circle and semicircle can be used in robotics. And the concepts of trigonometry allows us to find the width and the distance from a remote object. These applications simplify our navigation and aid in obtaining destination. The knowledge of mathematics helps to develop new concepts that makes the program accurate, consistent and reusable after year and year. Many of us understand these basic mathematical concepts but may not think of applying this knowledge to robotics. Here in this we can calculate the length reduction. Detecting the length of the object is useful for the navigation program. Here this mission is used to operate in a medical field. Usually doctors do operations. Here we can we are going to use a robot to perform the operation. Previously the function that detects blockages require bumping into the objects, marking it on the map and subsequently rerouting. Detecting the distance from the object and its length allows the program to completely avoid the object while also marking it as a blockage. This results in a faster and smarter navigation. Knowing the length of the object is also useful when the robot must grab or move it. It allows the robot to calculate how much it must open its arms or claws in order to pick it up. Now, grabbing objects using geometry. We apply mathematics to make programming and grabbing objects in robotics which much more efficient and reliable. Many missions involve performing the fundamental motions like lifting or reaching for an object. By applying geometry and trigonometry, we can create models that can be reused after year and year. Assume our robot has an arm consisting of two segments. The first segment can rotate 180 degrees and the second can rotate 360 degrees. We are going to derive a system of equations that allow the arm to grab any object within a semicircle made by the arm. Our objective is to bend the two segments or arms to reach a desired point A, B. Here A, B is the object we are going to grab. Here 0, 0 is the origin. Here two arms are going to perform R1 and R2. So for R2 draw a semicircle and for R2 draw a full circle. The locus of the arms lies on the coordinate plane. The first arm has a length of R1 and it rotates 180 degrees around 0, 0. The second arm, which extends from the end point of the first arm, has a length of R2 and rotates 360 degrees. The radius of the large hemisphere is R1, R2. Point A, B is an input of our program and it must lie within this hemisphere. The point labeled X, Y is the location of the joint of the arms. The first step is to solve for X and Y. After solving X and Y, we move each arm to the desired location to reach point A, B. To reach a point in the three-dimensional world, a coordinate X, Y, Z should be specified. We assume that we have navigated and spun the robot to a position and angle such that a point A, B is within the reach of the arm. Therefore, the third dimension or Z axis involves the movement of the actual robot. This simplifies our problem to a two-dimensional coordinate system. To find the unknown point X, Y, we will apply our knowledge of circles. The standard equation of circle is x square plus y square equal to r square. Here the h comma k is the center. So x minus h whole square minus y minus k whole square equal to r square, where h comma k is the center point of the circle. The radius is r and x comma y is any point on the circumference of the circle. The equation of our first circle is x square plus y square equal to r1 square. The equation of our second circle within the radius is x minus a whole square plus y minus b whole square equal to r2 square. Take it as first equation and second equation. It is possible to solve this equation algebraically. We may use a numerical method to find x comma y with this program. This is accomplished within a loop by plugging in values of x and y, finding the values that best fits the equation with the input a comma b. So moving on with trigonometry. Once we have decided x comma y, we first need to move the r1 arm to that point and then r2 arm to a comma b. We achieve this by utilizing our knowledge of triangles and trigonometry. Find the values of angle A and angle B. So using sin theta equal to opposite by hypotenuse, simple equation, angle A equal to sin inverse of y by r1. Here y is the y axis distance and r1 is the radius. So angle A equal to sin inverse of y by r1, angle C equal to sin inverse of a minus x by r2, angle B equal to 90 minus angle A plus angle C. Using r1 as the x-axis, rotate r2 using the equation r, angle B by 360 degree, where r is the circumference of the circle made by r2. We have completed our movement of the arms to reach point a comma b. We can use trigonometry also to find the object's distance away from the object. The ET sensor is the range distance sensor. It sends out a modulated frequency IR beam and measures the reflection to detect the distance from the sensor to an object. It returns an integer corresponding to the distance to the object. If no object is detected, a large value representing infinity is returned. The width of the object z is the only unknown value. Using law of cosines, z square equal to x square plus y square minus 2xy cos angle z. So from that we can calculate the angle of the object z. So trigonometry is also used in mechanics. So in this module we have seen about the suspension bridge, the concept of mathematics used in robotics and to calculate the distance away from the object. In the next module 2, let us see more examples related to hanging strings. Thank you so much for listening.